Hello friends. Now if you recall that we are discussing about the heat transfer phenomena in polymer systems under the edges of polymer process engineering, and we are going to discuss about the thermal properties and conduction in this particular lecture. Now before we go into the detail of this particular topic, then let's have a brief outlook that what we discussed previously. We discussed about the heat deflection temperature, we discussed about the Weichert softening temperature, then we discussed about the heat capacity, thermal expansion. We discussed about the thermal stresses and their importance in the polymeric system. We discussed about the thermal shock with the help of certain numerical examples, and we are going to discuss the melting point and the glass transition. Now here in this particular segment we are going to discuss about the melting temperature, the glass transition temperature. This is very important in the polymeric system. We are going to discuss this thing, and then the thermal conductivity and thermal conductivity, especially in the polymers and composites. Apart from this, we are going to discuss about the heat transfer and its heat conduction heat transfer, then how this conduction takes place in the polymeric system, and we will deal with the several heat transfer example pertaining to the polymers. Now let us talk about the amorphous and the crystalline polymers. The polymers usually made up of the long chain molecules, and that may be amorphous or crystalline. Now the structure of polymer is defined in terms of crystallinity. Amorphous polymers, they have the random molecular structure that does not have a sharp melting point. Also the amorphous materials soften gradually as the temperature rises. For example, like polycarbonate, general purpose polystyrene, polymethyl methacrylate, acrylonitrile butadiene styrene, all these are the best example of these polymers. Now the crystalline or semi-crystalline polymers, they have a highly ordered molecule structure. These do not soften as the temperature rises, but rather have a defined and a narrow melting point. Now this melting point is generally above that of the upper range of amorphous thermoplastic. For example, for the polyolefins, polyethylene terephthalate, polyoxymethylene, all these are the example of the crystalline and semi-crystalline polymers. Now completely amorphous polymers, they possess the glass transition temperature only, and there are the completely crystalline polymers, they possess only the crystalline melting temperature or point, and semi-crystalline, they possess both glass transition temperature and melting temperature. So in this particular figure you see that this is the schematic representation of the observed crystallization behavior of polymer. Here you see the amorphous range, this is the crystalline range, and if you change the temperature, you will observe this type of a behavior. Now crystallization TC, this occurs above the glass transition temperature at which the amorphous phase in the polymer system can acquire mobility. Now in the temperature ranges between the glass transition temperature and the melting temperature, that is during the crystallization process, the polymer chain from the amorphous phase of the blend tend to crystallize. Let us talk about the glass transition temperature, because in the previous slides we discussed about this TG. So when an amorphous polymer is heated, the temperature at which the polymer structure turns to viscous liquid or rubbery, this is called the glass transition temperature, the TG, and this is because of the polymeric chain, and they try to unentangle themselves to align in a particular flow behavior, and that occurs at the glass transition temperature. It is also defined as a temperature at which the amorphous polymer takes on the characteristics glassy state properties like brittleness, stiffness, rigid and difficult to bend, all these things upon cooling. It is named, glass is given because glass is a supercooled liquid, and this resembles in the amorphous polymeric structures. Now this temperature is usually measured in degrees Celsius. This depends on the chemical structure of the polymer and the chain structure, and they can therefore be used to identify the polymers, and this is directly related to the molecular weight distribution. So the value of glass transition depends on the mobility of the polymeric chain. As I discussed, that when you raise the temperature, they try to unentangle, and if you lower the temperature, they try to entangle themselves. And this is for the most synthetic polymers, they lies between 170 Kelvin to 500 Kelvin. Now here you see this is the Young modulus versus the temperature. Now here you see the glass transition temperature variation of different things, like this is the glass transition temperature and over the period of raising the temperature, the rubbery and the rubbery flow, and then the viscous flow. Now this is because if you raise the temperature, then all the chains they try to align themselves in a particular array and then they try to flow. So that's why these are the different stages if you raise the temperature from any stipulated point to a different point. Now this is, you see, the transition from glass to the rubber like state is an important feature of the polymeric behavior, as there is a dramatic change in the physical properties such as hardness, elasticity, all these things. And some polymers they are used below their glass transition temperature, like polystyrene, PMMA, etc., which are hard and brittle and their glass transition temperature are higher than the room temperature. So if you raise the temperature, again initially this is the glassy state. Glassy state is a subcooled liquid type of state. Then glass transition temperature where they aligned in the rubbery state, and this is the rubbery state, and then they try to go for the viscous flow. When some polymers they are used above their glass transition temperature, like rubber elastomers, polyisoprene, polyisobutylene, etc., and they are the soft and flexible in nature and their Tg are less than the room temperature. So this can be used as a soft material and for the various purposes, like different type of grasses, artificial grasses, then carpets, all these things, they are using this particular type of behavior. At glass transition temperature, changes in the hardness, volume, percent elongation to break of solid, they are mainly seen, and glass transition is an important tool to modify the physical properties of the polymer molecules. Now further, the improvement in the handling characters, solubility and reproducibility in the dissolution of the solid, this can be achieved during the increase in the glass transition of the solids. Sometimes like hard plastics like polystyrene, polymethyl methacrylate, they are used to below their glass transition temperature when they are in the glassy states. Now their glass transition temperature values are above room temperature and around 100 degrees Celsius. Rubbery elastomers like polyisoprene, polyisobutylene, they are used above their glass transition temperature as their rubbery state is required, or the soft and flexible character is required for those polymers. Now here you see the curve that is the specific volume versus specific volume as a function of temperature in the transition region. When a liquid polymer is cooled, the transition from highly viscous supercooled melt to the rigid glass begins at the temperature T. Here you see this one. Now this is T2, that the solidification process is terminated. The process is called the glass transition occurs because the amorphous polymer exhibit a change from soft elastic above glass transition to the glass like below glass transition temperature. So the motion of all the polymeric chain starts the cessation. Now this the glass transition temperature or Tg is a point which the tangents of the two curves, here you see that the two curves intersects and the slope indicates the transition or intermediate state where the liquid rubbery glassy state are coexist in equilibriums. Now how to measure the glass transition temperature? By observing the variation of some thermodynamic properties with the temperature like a specific volume. Now if we are having a plot or a figure, this the slope of the specific volume versus temperature increases above the glass transition temperature. The value of Tg determined in this fashion will vary slightly with the rate of cooling and heating. So this reflects the fact that long entangled polymer chain cannot respond instantaneously to change in temperature and elasticity because they are bulky in nature, and the difficulty in the making thermodynamic measurement on the polymer. The most usual test method to determine the glass transition temperature of the polymer is DSC, that is differential scanning calorimetry, and differential thermal analysis, DTA. So in DTA, the difference in temperature between the sample and a reference material is monitored against time or temperature, while the temperature rise or fall the sample in a specified atmosphere is programmed. Now in DSC, the difference in heat flow to a sample and to a reference is monitored against the time or temperature, while the temperature rise or fall of the temperature in a specified atmosphere is programmed. Let us talk about the DSC, that is a differential scanning calorimetry. DSC measures the heat flow into or from a sample as it is heated, cooled or held under the isothermal condition. There are various applications of DSC. This includes the polymers, fibers, elastomers, composites, film, pharmaceuticals, food, etc. This DSC provides the different important properties of the material like glass transition temperature, melting point, heats of melting and crystallization, crystallization time and temperature, percent crystallinity, compositional analysis, heat capacities, thermal stabilities, all those things. Now let's a brief sketch or a rough sketch about the differential scanning calorimetry. This DSC apparatus broadly consists of a furnace, the temperature sensor, the test chamber environment, the temperature controller, recording device, sealed pans, balance, etc. So this is a sample pan. Here you can put the polymer sample, and this is a reference pan, and all these things are programmed. Now, there are various terminology being used, the DSC. The first order transition, in the first order transition, there is a transfer of heat between the system and surrounding, and the system undergoes an abrupt volume change, that is a melting point and crystallization temperature. So here you see this is the temperature, the crystalline solid melt, and this is the crystalline first order. Now, second order transition, in the second order transition, there is no transfer of heat, but the heat capacity does change. The volume changes to accommodate the increased motion of the polymer chain, but it does not change discontinuously. Now, when we plot the glass transition temperature, the TG, the property usually TG in graph, this provides the property of the amorphous region. Below glass transition temperature, disordered amorphous solid with immobile molecules, and above glass transition temperature, the disordered amorphous solid in which the portion of molecules can move back and forth. The second order transition, this increase in heat capacity, but there is no transfer of heat. The above glass transition temperature, the polymers are in mobile condition. When they reach the rigid temperature, they gain enough energy to move into very ordered arrangement, which is we call the crystals. When polymer fall into these crystalline arrangement, they give off heat. When this heat is dumped off, there is a drop in the heat flow as the big dip in the plot of heat flow versus temperature. So above TC, or if we talk about the melting temperature, so above TC we reach the polymer's melting temperature, or TM, those polymer crystals begin to fall apart, that is they melt. So melting temperature is quite essential, that the chains come out of their ordered arrangement and begin to move around freely, and melting is a first order transition. Now here you see this is a table which represents the difference in TGA, DTA and DSC. Now TGA, this is thermal gravimetric analysis, differential thermal analysis and differential scanning calorimetry. This TGA utilizes the technique of the change of the mass of a sample with the change of the temperature. This is usually observed and analyzed, wherein DTA, the temperature difference developed between a sample and a reference compound which is measured, and identical heat treatment is being carried out. The DSC, the heat flow is measured against the temperature change at a particular time. Then the compound analyzed. What compound we analyze? This used to analyze the inorganic material, metals, polymers, plastics, ceramics, glass, composites, etc. And in DTA, they used to analyze the thermal properties of the minerals for the characterization of the polymer and biological materials. And DSC, they used to analyze the protein, antibodies, etc. Now, nature of sample is again very important. Then the sample can be used as a solid substance in TGA, whereas the solid substance, again this can be used in DTA, and in DSC the sample is always in a liquid form. Now, let us talk about the various factors affecting the glass transition temperature, like chemical structure, molecular weight, molecular structure, polarity, chemical cross-linking. Apart from this, the plasticizer, water or moisture content, enthalpy and entropy of individual polymers, pressure and free volume, chain flexibility, steric hindrance, copolymerization, all these factors, they affecting the glass transition temperature. Let us talk about the chemical structure. The molecular weight is directly proportional to the glass transition temperature. So the increase in the molecular weight, say up to 20,000, value of Tg also increases, but after this particular triggering value, Tg is unaffected because Tg reaches a limiting value. There is a relationship between the glass transition temperature and the molecular weight. This is given by the P.J. Flory. Now here the Tg is equal to Tg infinite minus k over m. The k is a constant and m is the molecular weight, and 1 over Tg is equal to 1 over Tg infinite plus a over m, where a is constant. So Tg infinite is the maximum glass transition temperature that can be achieved at a theoretical infinite molecular weight. Then the molecular structure. Insertion of a bulky inflexible side groups. This increases the glass transition temperature of material due to the decrease in mobility of those chains. Then the chemical cross-linking. This increase in the cross-linking decreases the mobility. This led to the decrease in free volume and increase in glass transition temperature. Some sort of the polar groups. The presence of the polar group, this increases the intermolecular forces, interchain interaction, cohesion, this leading to the decrease in the free volume and resulting in glass transition temperature. Sometimes addition of the plasticizer plays a very vital role. The plasticizers are low molecular weight, non-volatile substance like dibutyl phthalate, dioctyl sebacate, methyl salicylate, methyl acetate. Now, addition of plasticizer increases the free volume in the polymer structure, and this plasticizer gets in between the polymer chain and move them apart from each other. Now, this results in the polymer chain in sliding more easily. So, as a result, the polymer chains can move around at a low temperature, resulting in decrease in Tg of a polymer. Water content and entropy also plays as a valuable factor in affecting the Tg. The water or moisture content, this increase in the moisture content helps in the formation of hydrogen bond that increases the distance between the polymer chain, hence the increase in the free volume and decreases the glass transition temperature. Effect of entropy. The value of entropy for amorphous material is higher and low for crystalline material. If value of entropy is high, the free volume increases and the value of Tg decreases. The pressure and free volume also plays a vital role. The increase in pressure of surrounding, this leads to decrease in free volume and ultimately high glass transition temperature. The chain flexibility. The polymer with a linear chain, this mainly consists of CC or CO or CN bonds. They possess the high chain flexibility, therefore shows a low Tg value, and usually minus 125 degrees Celsius for polyethylene. This is for the sake of an example. The presence of aromatic cycle ring in the backbone chain reduces the flexibility and thereby increasing the glass transition temperature. Sometimes steric hindrance is also playing a very vital role. The presence of larger and bulky group on the polymeric long chain, this restricts the degree of freedom and free rotation, hence the Tg value increases. Ortho position restricts the rotation due to the steric hindrance more than the para and meta position, therefore the Tg value is higher. Let us talk about the melting temperature, the temperature at which the molecules transition from a rubbery state to a melt state. Usually it is called the melt temperature or Tm. This simply melting temperature is the temperature at which the phase transition occurs. For example, solid to liquid or a liquid to vapor, or it can be set to the melting temperature TEM. This is a temperature at which the transition from the crystalline to semi-crystalline phase to a solid amorphous phase takes place. The crystalline polymer is a discontinuous change in specific volume at Tm. This is as per this figure. Now, for amorphous polymer, the change is continuous. No melting temperature is observed, but there is an increase in the slope at glass transition temperature. For semi-crystalline polymer, intermediate to crystalline or amorphous, and this shows the melting temperature and a glass transition temperature. So, there is a relationship between the glass transition temperature and a melting temperature. This is for the symmetrical polymer, Tg is equal to Tm over 2, and for the non-symmetrical polymers, Tg is equal to 2Tm over 3. Now, there are various factors affecting the melting temperature. Usually the same factor, they affect the glass transition temperature and the melting temperature. Usually high glass transition temperature, the high melting temperature are found together, and vice versa. High polarity and hydrogen bonding, this increases the melting temperature. Molecular symmetry also led to the high melting temperature. Let us talk about the thermal conductivity, K or lambda, the rate at which the heat is transferred by conduction through a unit cross-sectional area of a material when a temperature gradient exists perpendicular to the area. The coefficient of thermal conductivity, this is the K factor, usually is defined as the quantity of the heat that passes through a unit cube of substance in a given unit time when the difference in temperature of two factor is 1 degree Celsius. Now, this is the mathematical representation of the thermal conductivity K, where Q is the amount of a heat passing, A is the area of the cross section, delta T is the temperature difference, and T is the thickness of the specimen, and usually thermal conductivity represented as K. So, this is measured in BTU per hour square feet degree Fahrenheit. This indicates the material's ability to conduct the heat energy. The significance of thermal conductivity is the particularly important in the applications such as headlight housing, pot handles, hair curlers that require a thermal insulation and heat dissipation properties. Now, computerized mold filling analysis, the program, this required a special thermal conductivity data derived at high temperature than a specified mold text. There are various factors affecting in the thermal conductivity. One is the crystallites, they have the higher thermal conductivity. Now, as the density of the cellular plastic decreases, the conductivity also decreases up to the maximum value and rises again due to the increased convection effect caused by the higher proportion of open cells. Now, let us talk about the correlations. Anderson and Knapp, they have summarized the most of the available polymer thermal conductivity data. In many instances, such data are not available. It is therefore become necessary to use certain correlations for estimating the needed information on thermal conductivity measurement in polymer. So, in the region above the glass transition temperature, correlation required Tg for the polymer and thermal conductivity at Tg. This can be bypassed if one thermal conductivity is known at a given temperature. So, this is the mathematical representation through which you can develop the correlation, that is K is equal to 6.3 into 10 to the power minus 3 into 1 minus 0.00015 into T minus Tg over Tg to the power 0.216 into m to the power minus 0.3, where K is the thermal conductivity, which is represented in calories per centimeter second degree Celsius, m is the polymer molecular weight, and T is the given temperature. Now, this graph shows a relation between the thermal conductivity at any given temperature to the thermal conductivity at glass transition temperature versus the ratio of given temperature to the glass transition temperature. Now, in starting, there is an increase in the temperature, thermal conductivity ratio increases, and after attaining the optimum level, there is a decrease in thermal conductivity ratio with increase in temperature. Let us talk about the another correlation, which is through the graph. For amorphous solid polymers below glass transition temperature, it is found that K correlates well with the refractive index, and such correlation, this can be used to get the value of K at a given temperature. Now, this particular graph was determined by taking a certain temperature like T1, T2, T3 and so on, and then calculating the thermal conductivity using the previously studied correlation. So, with increase in the refractive index, thermal conductivity of the polymers are decreasing. Another correlation with respect for the thermal conductivity, these values of the solid semi-crystalline polymers can be estimated by the method of Ironman. This involves the relations Kc over Ka minus 1 is equal to 5.8 into rho C over rho A minus 1, where this Ka and Kc, they are the thermal conductivities of the pure amorphous and crystalline state, so that can be used as a reference material, and rho A and rho C is the corresponding densities. So, the previously studied correlation, this can be used in conjunction with this particular figure to estimate the thermal conductivity for a polymer of a known crystallinity. Density of crystalline part rho C, this is directly proportional to rho lambda A over lambda C. So, therefore, the density of the crystalline material increases the thermal conductivity of amorphous part lambda A. This also increases while the thermal conductivity of crystalline part is decreased with lambda C. Another correlation, and that is the molten polymer thermal conductivities. This represent somewhat different case than that of a solid phase. So, the essence of thermal conductivities of the melt polymer vary little with the temperature, and consequently the acceptable value of K, this can be estimated from the relation, that is K is equal to 1.2 into 10 to the power minus 2 Cp into rho to the power 1.33 into m to the power minus 0.3 over Tm to the power 0.216. This Tm is the melting temperature, and degree Kelvin, Cp and rho are the values of specific heat and density of the melt. So, if the values of both rho A and rho C or Ka or Kc are not known, a correlation of the type shown in this particular figure can be used to estimate the K or thermal conductivity at a given temperature. All that is needed, that is specific heat and density at a room temperature. Correlation number 5, the effect of orientation of the solid and the resulting anisotropy is given in the review paper given by the Anderson and Knapp, and this usually utilizes the pressure effect, and the pressure effect generally can be handled as in this particular mathematical relation. dk over dp is equal to khp 5.25 beta, where beta is the isothermal compressibility and khp is the high pressure value of thermal conductivity. Now, let us take some of the examples of thermal conductivity. Now, here is one question, that it is given that the thermal conductivity for polymethyl methacrylate is 5.2 into 10 to the power minus 4 calorie per centimeter Kelvin at 25 degrees Celsius. So, what will be its value at 200 degrees Celsius? So, obviously require certain statistical data, and that is at 25 degrees Celsius, T over Tg is equal to 0.77, and at 200 degrees Celsius, T over Tg is equal to 1.22. Now, you can utilize this particular graph to find lambda T over lambda Tg. Now, as T over Tg is 0.77. So, to obtain the value of delta T over delta Tg, we should first go through the x-axis using a scale bar determining the value of 0.77. For your convenience, it is already marked in this particular figure. Then we will trace the vertical line from this value to the point where the dark circle of the point of the polymethyl methacrylate is indicated, and then we will trace the horizontally to obtain the desired value, which is determined as 0.96. So hence the value of lambda Tg, this can be determined as K, this is equal to 0.96, 5.2 into 10 to the power minus 4 calorie per centimeter Kelvin over K, which is comes out to be KT 5.4 into 10 to the power minus 4 calories centimeter, this one. Now, as we have obtained the value of thermal conductivity at the glass transition temperature, we can use this value to obtain the thermal conductivity of a material at any temperature, if the ratio between the temperature and the glass transition temperature is provided. So, if you look into the question data, you will find that at 200 degrees Celsius, T over Tg is given as 1.22. So, therefore, we will again use the same graphical tracing strategy to obtain the value of lambda T over lambda Tg at 200 degrees Celsius, that is 200 plus 273, 473 Kelvin. So, here you see that this value is given over here, and by this way you will find that this one is 0.95. Now, thermal conductivity at 200 degrees Celsius is given as K 473, this is K 473 Kelvin, 5.4 into 10 to the power minus 4, which is comes out to be, which is equal to 95 as we calculated in the graph. So, K equal to 5.1 into 10 to the power minus 4. This is the answer. Let us take another question. What is the thermal conductivity of a polystyrene at 496? Now, it is given that the molecular weight is M is equal to 104.5 and glass transition temperature is 373 Kelvin. Now, here you can use the formula which we have already discussed, that is K is equal to 6.3 into 10 to the power minus 3 into 0.0015 into T minus Tg over Tg to the power 0.216 m to the power minus 0.3. So, just only you need to put the values, and this is 6.3 into 10 to the power minus 3 into 1 minus 0.00015 into 496 minus 373 over 373 into 0.216 into 104.5 to the power 3, which is comes out to be 4.2 into 10 to the power minus 4 calories per centimeter Kelvin second, and this is our answer. So, dear friends, in this particular segment, we discussed the various aspects of thermal conductivity with a couple of examples, and for your convenience, we have enlisted various references, and these references are very useful for further studies. So, in case if you wish, you can utilize these references for your further studies. Thank you very much.